Hello everyone and welcome to today's graph reading group.
And today we discuss Timewarp, and to me, amazing paper that accelerates molecular dynamics. Let's go.
Yep. So this is a paper that I worked on with Leon and many others. So let me just show you who they are. So Leon is the first author, and then joint first author with himself are me, Tor, and Bruno, who all worked on this while we were at Microsoft. And also Mark Brockschmidt, Sebastian Noetz, and Frank Noah, and Ryota Tomioka. And this is in collaboration with also the entire AI for Science team at Microsoft, which is interested in problems like this one and many others besides. So let me get started on the actual problem. So let me talk about something that probably you all know a lot about, molecular dynamics. So molecular dynamics tries to simulate the stochastic motions of molecules, and here's a little human protein wiggling around in some simulation. Typically, when you do MD simulations, you integrate Newton's laws of motion, use a small time step, roughly a femtosecond is quite common. And there are problems with this kind of approach to simulating biophysical processes. For example, often you're interested in timescales of like a millisecond. So that is 10 to the minus 3 seconds, and that is just far too long most of the time to handle with this approach. Secondly, we're not transferring information with this approach. So every time you do a new MD simulation with the same force field, it's as if you are running the first MD simulation ever made. You forget everything you've learned in the 100 other MD simulations you've run and all the compute you poured into that, and you run a brand new thing. So you're not transferring what you know. And in a machine learning sense, you're kind of wasting information. You're not exploiting the data you generated previously. And because of this, well, partly because of this, MD simulations consume much of the worldwide supercomputing resources. The question we want to ask with Timewarp is, can we tackle some of these problems with a deep learning approach? So just some recap about the Boltzmann distribution. Many applications in MD boil down to sampling from the Boltzmann distribution. It represents equilibrium distribution of a molecular system or physical system at some temperature. And it's given by the way, can you guys see my cursor as I move it around? Yeah, so it's given by e to the minus u over kt, where that's the density and u is the potential energy function. And yeah, so sampling IID from this distribution is intractable even if you know u. So how are we going to tackle this problem? Traditionally, we'd run a long MD simulation, and asymptotically, the result of that MD simulation will be a sample from the Boltzmann distribution. But we've already said that this is often too time-consuming. What we're going to do is take a detour and instead think about a different object, which is the conditional distribution. So we want to sample from this unconditional distribution mu, but let's first consider a time conditional distribution where we consider the state of the system at a time t and distribution of that state at a time t plus tau. Tau is some finite time step in the future. So you can imagine starting at some time t, there are many possible locations, x of t plus tau, the system could end up with because there's randomness in the system due to thermal fluctuations. And this conditional distribution tells you what the distribution of the outcome is going to be. What we're going to do is try to speed up molecular dynamics by proposing large time steps tau, where tau is much, much greater than delta t, where delta t is the integration time step of roughly a femtosecond. What we want to do is also make it unbiased in the sense that we're going to correct the samples that we propose using Metropolis-Hastings corrections. And we're going to learn to propose large steps on a data set of many trajectories. The hope is that we'll be able to transfer between these different trajectories. And here I'm going to show a little example of what that looks like. So we have a tiny little peptide here on the left, representing the positions of the atoms at time t. And then here we take tau to be 500,000 femtoseconds. So which is 100,000 times longer than the time step delta t for this particular simulation. This is 50,000 femtoseconds. And then the model proposes immediately a new state. And this new state is you can see it's actually rotated and it's in a different metastable state compared to the original state. And what I'm showing here are actual states proposed by the model. So this is what we want to achieve. And how are we going to do this? We're going to need an appropriate data set to train our model on. So what we did is we generated long MD trajectories on a collection of small peptide systems. So imagine here, I'm showing a schematic which represents one of these trajectories. We simulate them using classical MD techniques. We use the amber force field, and we use the OpenMM package to simulate these.
If you say the amber force field, which do you mean specifically? Like there are these different options for the force field itself, or for the protein itself, dipeptide, and then for the water, which ones did you use?
Yeah, it's amber 14 and implicit water we are using.
There are also multiple implicit ones, no?
The one that OpenMM uses. So there's only one, amber 14.
Okay. Okay.
Yeah,
Is it actually a big difference what these force fields produce on average, so to say?
No, they're quite similar, but you'll notice subtle differences. For example, some metastable states might be more or less likely compared to another force field.
Okay.
I'd say there's a big difference between implicit and explicit water models, right?
Sure.
But one limitation of what we did was everything was done implicitly to make it simpler because we didn't have to model the waters.
Okay.
Yeah. So here's like a trajectory of the molecule evolving with time. And you can imagine using classical MD, you get tiny little time steps delta t each time. What we're going to do is subsample this trajectory at a frequency tau, where tau is much greater than delta t. So you can imagine a big step in the orange arrow. Then we're going to train the model to predict x of t plus tau given x of t. So the model doesn't predict a short time step in the future, it predicts a huge time step into the future. And we're going to split our data set into train and test peptides. So we generate many trajectories with many peptides. Some of these peptides we put in our train set, some of these peptides we put in our test set. So the entire trajectory will be held out. Our goal is to speed up sampling on the test peptides. And when we say speed up, we mean speed up relative to molecular dynamics. So we want our model to, when shown a test peptide, be able to sample from it faster than if we were just running MD from scratch. So let me just list a few desiderata that we want from our model, given, I guess, the motivations that we had earlier. We want to be able to sample quickly. So we want fast sampling so we can quickly generate these trajectories using our model. We want to have a tractable likelihood so that we can do Metropolis Hastings corrections. We want it to be transferable. So train on a train set and test on a new test set of different proteins. And I guess, connected to that, we want to incorporate the symmetries of the physical system, or at least we want to incorporate some of the physical symmetries. And because of these reasons, we settled on using conditional normalizing flows, and we will see that they managed to handle most of these desiderata. So just to recap, mu is the true conditional distribution. We approximate it with a learnable parameterized conditional distribution p theta. We're going to use a conditional normalizing flow where we sample z, the latent variable, from a standard Gaussian, and then we define the output as some bijection applied to z, but that bijection itself is parameterized by the initial state x of t. So if you think of it this way, this green box in the middle is a bijection. The bijection is between the noise sample, the latent variable, and the output, which is a predicted state. But the parameters of the bijection, I guess the bijection itself is controlled also by x of t. And the map from z to x of t plus tau must be invertible because it's a flow. But the map from x of t to x of t plus tau can be anything. It doesn't need to be invertible. And we have a tractable formula for the density using the change of variable formula, as with normal normalizing flows. So normalizing flows, if we use a real MVP architecture, at least we'll have fast sampling. And they give us a tractable likelihood, sort of by definition of a normalizing flow. And at this point, we're going to go a bit deeper into the conditional flow architecture. So what is the architecture we're going to actually use? And to some extent, this is a matter of trial and error and seeing what works and what doesn't. But this is sort of what we ended up settling on for the paper. And it's got three hierarchies to it. The first level on the left here is that we're using a real MVP architecture where you have scales and transforms of some of the variables based on the others. And each of the modules in the real MVP is going to be controlled by something that we call an atom transformer, which is basically a transformer that we apply to atoms. And the only difference between the atom transformer and a normal transformer is that we're going to use a special kind of attention, which is a very simple attention that takes into account the distances between atoms. And I'm going to look at each of these panels one by one, just to give a clear idea of actually what goes into each of these. It's important to note that we're working throughout with an all atom representation. This allows us to easily compute the energies using Amber, which in turn allows us to compute Metropolis Hastings except reject steps. And we're working in Cartesian coordinates. We do not use internal coordinates at any point. We wanted to do this to make the model general as possible. Yeah.
Can you maybe lose a few words? What do you mean with this? I imagine some people don't even know what you mean with internal coordinates. So why this comparison between internal and all atom is important, and what internal coordinates you know?
Yeah, so internal coordinates would be you would identify certain coordinates that that in some way
I would just go with the example of torsion angles.
Yeah, so yeah, the classic example here would be torsion angles. So like which represents like how each part of the peptide is rotated relative to the other parts. And in the case of the simple peptides we're looking at, if you already use the torsion angles and you just sample in that space, I believe the problem is already nearly solved by using this domain knowledge. And we wanted to not use this domain knowledge and have things learned from scratch. I don't know if Leon, you can give maybe a better explanation than that.
And right, this is pretty cool because then it could also work for larger molecules. Yeah,
so we're trying not to. So we are working on very small molecules, but we're trying not to take advantage of exploiting the fact that they're small to basically already solve the problem by writing down variables of like the kind of transformations that are interesting. But yeah, Leon, do you want to say something?
Oh, there's also a question that internal coordinates would prohibit us from predicting rotations. So it depends on the choice of internal coordinates. If you, for example, choose what's usually chosen, and I think you discussed Boltzmann generators as well, and there they use bond distances, angles along bonds, and these torsion angles. And these are actually rotation invariant. So there, these invariances would already be baked in. But the big problem is that these internal coordinates are quite specific to the molecule you're looking at. So the model is harder to make transferable.
And also, Clemens, here we don't care about predicting rotations necessarily, right? Like every thing that you predict, no matter how it is rotated, it will have the same energy and the same probability. And yeah, I think this point maybe is the most important one that Leon just made, that if we use internal coordinates, then also we're not able to generalize. Like if we use internal coordinates that are specific to one molecule, like that its torsion angles, then we're not able to generalize to new molecules. Yeah, anyway, I think enough on that topic. Let me not stop you anymore from talking about the flow.
Yeah, so yeah, basically we try to keep things as general as possible, and all atom Cartesian is about as general as you can represent these molecules. So let's talk about each individual part of the architecture. So I'm going to focus first on the real MVP part. So I'm sure you know a real MVP defines an affine transformation of some of the dimensions based on the others. And what we're going to do is we're going to have a model that outputs two kinds of quantities, the positions and the velocities. And since we're going to output two kinds of quantities, we're going to have two kinds of latent variables. In practice, we just split the vector into two parts. One part of the latent variables will to represent the positions and one part to represent the velocities. And we're going to implement the real MVP by transforming the positions based on the velocities and vice versa. So usually in real MVP, you make a somewhat arbitrary division between the two. You divide the latent variable arbitrarily into two disjoint sets, and then you perform these transformations. But here we intentionally do it based on the positions and the velocities And this turns out to be quite convenient for us. And each transformation is going to need to output a scale and a translation, just like any real MVP. And we're going to parameterize this by what we call the atom transformer. And we're going to stack a lot of these, as with normal flows. One more thing to note is that our flow does not directly predict the output. It predicts the change in the input to produce the output. So it's maybe like a residual model in that sense. And then now let's talk about the atom transformer that I've mentioned already. So the atom transformer, it looks a lot like a regular transformer. And the way the forward pass works is that you concatenate the latent variable Z and the conditioning state X of t. So remember that this model has two inputs: the latent variable, which eventually gets bijected into the predicted state, but also the conditioning state, which can affect the bijection in some arbitrary non-invertible way. And what we're going to do is we're going to take the latent variable, here represented by Z, and concatenate it with X, which represents the conditioning state, and also H, which is a feature embedding of the atom type. So oxygen will have a different kind of embedding from nitrogen and a different kind of embedding from carbon. We're going to pass this, this set of vectors through multiple transformer blocks, just like the transformers, more or less, and attention is all you need. Except we're going to use kernel self-attention instead of the usual dot product attention. And just with normal real MVPs, we're going to output a scale and a translation factor. One thing that's worth noting is that in comparison with language models, we're not going to have a positional embedding, because it's not as if all the atoms are in a sequence. So having a linear sequence embedding doesn't really make sense. And also the 3D position of the atoms is already encoded in the values here. So the model knows what a 3D position is. It doesn't need to obtain a separate sinusoidal position embedding. Okay, so now let's explain what this kernel self-attention is. So kernel self-attention, basically all we're doing is putting a Gaussian RBF on the inner atomic distances to compute the attention weights. So the inductive bias that we want to incorporate here is that nearby atoms should have a greater effect than faraway atoms. So basically, let's say you have an atom I and an atom J. You take the position of atom I, you minus the position of atom J, you take the 2 norm, and then you exponentiate it with a minus sign. And then that gives you how much attention that I pays to J. And we also implement a multi-head version of this. So each head is going to use a different RBF length scale. So it's just like multi-head attention with dot product attention, except now it's this kernel attention, and you use a different length scale for every head. So just to recap. Oh,
wait a second, and like, are these components really important for your performance, or is it like it maybe gives a 5% improvement in terms of, I don't know, the width of your kernel?
Yeah, I don't think these are of fundamental importance. So the reason this was introduced in the end was because we started by using standard dot product attention, and then we switched to this, and it's much cheaper, the dot product attention, so it's faster. And in the early stages of development, at least, it performed as well as dot product attention. So we thought, might as well switch it out. And I could imagine, and yeah.
Compared to other architectures that are maybe slower, but more like build in more physical priors, or other architectures that are faster and
yeah, so we did try a bunch of other architectures. And Leon, maybe do you want to talk about what happened with at least TorchMDNet?
Yeah, so as Andrew mentioned, we tried different things. For example, TorchMDNet, and the results were not better, so very similar. And then we stuck with this architecture because it was quite fast to evaluate, which was important. So other methods tend to be slower and produced, at least back then, the same results.
Yeah.
But there's probably a lot to gain with using different, maybe, yeah, and somewhat different architectures, in our opinion.
So Jason Yim has a question. Did we try other architectures like E3NN? We did not try E3NN specifically, right, Leon?
Yeah.
I don't know. I'm actually not super familiar with the E3NN architecture and how that differs. Was attention important for performance?
I guess that's answered, right? With you. No.
I'm sorry.
I guess that's answered by saying like you tried other architectures, or you tried switching out the attention. But no, I think there's more to be said, maybe.
Yeah, I mean, so we did try various kinds of attention, kernel self-attention and the dot product, and also some other things ended up being tried.
Yeah, but I guess the question I would have mostly here is the all atom view important, or could you also have something more local? But also, I guess if you don't have this many atoms in your tetrapeptides, maybe that's enough atoms to make it.
Right. So are you asking, like, is it necessary to have full dense like squared attention?
Exactly.
So we also thought we also at one point introduced a cutoff where you only attend to a sphere with a certain radius. Yeah, I think for various reasons we didn't stick with that, and I think the main reason was that the peptides we were looking at were small enough that n squared attention was viable, and we also did use a graph neural net instead of n squared attention at one point, and attention was better. N squared attention was better than using a graph neural net defined by the chemical bonds. So it seemed that being dense didn't hurt, at least. I think there was a marked improvement switching away from GNN and towards transformers. Jason also asked why a positional embedding would not help. Okay, I think I should rephrase. It's not obvious that it wouldn't help. It could help the model to know, where you are along the backbone, for example. That could be useful. Although in principle, that kind of information can be derived from the all atom representation. So we could feed it to the model as another representation that might help it learn, but it's different from the case of language, where if you don't give it a positional representation, positional embedding, it has absolutely no way of figuring out the ordering of the words. At least here, we give it such a fine-grained representation that it could figure out the backbone if it had infinite training capacity. But whether feeding it in separately would help with learning is a separate empirical question that we did not test. At least Leon, I don't think we ever tried testing this. Okay, we got another question. Is the kernel attention computed on the full token or only a latent variable? So actually we use it only applied to the conditioning state. So whether you attend to another atom depends on how close you are to that other atom in the conditioning state. We could also apply it to the latent, we could imagine applying it to the latent variable, but it actually evolves during, in every layer in such a way that it becomes non-trivial to make that play nicely with the real MVP construction, right, Leon? That's sort of what we look into.
Invertibility becomes an issue if you attend to all of this. Yeah. So this is definitely possible, but only in a limited way.
Cool. If that's all for now, we'll.
If I can jump in quickly,
sure.
to add something. Many things were discussed right now. For example, like using attention instead of graph neural network. I don't think it's surprising at all to see the differences in performance, because when you look at the dynamics, you look mostly at interactions that happen outside the graph. So forcing all the messages to go through the graph just doesn't make sense. Using the attention weight being like Gaussian kernels instead makes a lot of sense from a physical point of view, because it adds a bias about proximity that the dot product self-attention does not have and will have to learn completely. adding the position of the backbone or using other kind of like, let's say, eigenvector positional encoding could, in my opinion, help improve the result. But as you said, maybe not having it forces the network to learn what's the backbone by itself. And maybe this leads to better generalization because the network has to go through more advanced thinking into like what's going on. But yeah, it's a nice hypothesis to test, like whether more positional encoding will help. I don't think they would hurt, but maybe they don't help. Yeah, that's what I wanted to add, but thanks a lot for the discussion.
Yeah, I agree with all those points. And yeah, I think with the positional encodings, that seems like an empirical question to me, what that will do or won't do. Okay, I'll move on if there's nothing else. Okay, so in theory, we have most of our desiderata. So the bottom left box, I've checked it because this transformer architecture, the nice thing about it is that you don't need to specify in advance how many atoms your protein will have. So at least in theory, you could feed it different kinds of proteins and at least the forward pass would run. In terms of incorporating physical symmetries, our model is not rotationally equivariant, and this is something that we tried at many points to address, but we never got around to making it work happily for us. But at the very least, it is permutation equivariant because of the transformer architecture. I see there's a small question in the chat. What features were used to define edges in the GNN experiment? When we did the GNN experiment, the edges were defined by what was bonded together. I guess as Dominique said, maybe that makes very little sense when we want to model dynamics. So, okay, moving on. Okay, so now let's think about how we're going to use this in an MCMC scheme that is asymptotically unbiased. So of course, our network can learn stuff, but maybe it will learn rubbish. And how are we going to know whether what it's outputting is actually physically meaningful? So the first thing to note is that in practice, we only care about the positions of atoms, not their velocities. And because of this, what we're going to do is replace the physical velocities with auxiliary variables that we draw from a standard normal distribution. So we don't want to model the velocities directly. They're not actually that interesting. We just want to model the marginal distribution of the positions. And so what we're going to do is define an augmented Boltzmann distribution that has the correct marginal for the positions, but the wrong marginal for the velocities. Yes, I see a hand.
Yeah, I don't understand why you say that you don't care about the velocities. Like if you, yeah, go. Okay, can you explain why we don't care about them?
So to some extent, this is like scoping the problem, okay, no, actually, the reason we don't care can be explained in the following way. So in the Boltzmann distribution for the joint distribution of the positions and the velocities, the velocities end up independent of the positions, and they are Gaussian. The variance can be computed analytically as a function of temperature and also the mass of each atom. So if you can model the positions, you can trivially sample from the joint of the positions and the velocities. So there's basically no learning problem in learning the velocity distribution. Yeah,
okay, I understand that, but like in the case of predicting the dynamics, if you want to predict t steps, like a time step in the future, if you don't have the initial velocity and you only have a distribution of velocity, you will not end up at the same point than the molecular dynamics.
Yeah,
right?
so this has to do with dynamics, and I guess like we somewhat scope the problem a bit to mainly target the Boltzmann distribution as our final goal. Like, so if we can sample from the Boltzmann distribution, we're happy, even if we don't necessarily have a model that can, for example, handle kinetics along the way.
Okay.
Yeah.
Okay.
So,
okay, I see.
Yeah, and in some ways, the MCMC procedure reflects this because, you know, MCMC, the chain asymptotically will give you the samples that you want, but, you know, you end up rejecting some samples and the dynamics of the chain are not necessarily physically accurate.
Yeah, okay.
I guess that answers this question, right? That here our goal is to sample from the Boltzmann distribution, and so we just don't care about the velocities or having, we don't care about the velocities, and you just use them as auxiliary variables and you call them velocities. Maybe
Yes,
we could
indeed.
call them something completely different.
Yeah.
But maybe one could also like have a little bit of correlation between the velocities and not completely resample them to have sort of a direction to your MCMC chain, and then have maybe faster mixing if the velocities aren't always completely resampled. But the point that you made is maybe something that I would be very interested in hearing a little more about. That we can just always, like, to sample from the Boltzmann distribution, we can just sample coordinates, and then we can always, like, arbitrarily, just based on the temperature, sample velocities.
Yeah.
So this is kind of remarkable. Like, I don't know, do you have more to say about this?
Yeah, I think it is kind of a very interesting property of statistical physics that in the exact Boltzmann distribution, the velocities are totally independent of the positions. I don't know, maybe with somebody with better physical intuition than me can derive some kind of lesson from that. But to me, it's just, it just falls out of the math, and it tells you that the learning problem for sampling really is all on the positions. All the action happens there. The velocity stuff is just trivial in comparison.
Yeah. I can try to explain a bit. Like there's if you look at it the classical way, because of atoms vibrating in many different directions, like suppose you start at a point here and the atom just like moves in different directions, right? And in the end you get a Gaussian probability of, like, let's say the different circles here that determine like the density, like of your probability of being somewhere, and the velocity goes like accelerating and then decelerating and so on, like at all times. So so it means that, like, in the end, like they both have their own distribution that is like not necessarily related. That when you take a position in the center of the sketch that I drew, like it can be coming from any direction with any speed. And another way is just like from the quantum mechanical perspective, you can just look at like the Heisenberg uncertainty principle, right? Where like you cannot determine both the speed and the position like accurately at the same time. If you get the exact position, you have absolutely no idea what the velocity is, and if you get the exact velocity, you have no idea what the position is. And this is like a fundamental thing in quantum mechanics. So like both way of explaining things should help here.
Yeah, I mean, my view is that this should be explicable on purely classical means, because the only thing you need to derive this result is the canonical ensemble, which itself comes from an assumption about uniformity of distribution over phase space in classical phase space, and then the form of the Hamiltonian, which is separable. And really, it's the separability of the Hamiltonian between the potential part and the kinetic part that allows you to obtain this independence factorization. Okay, but in any case, the relevance of time warp is simply that we do not consider learning the velocities as part of our goals. So we will just feel free to replace that distribution with anything we want.
But something like at the beginning of the presentation, you mentioned that your goal is to move the molecular dynamics 10,000 steps at a time. But here, like, your goal is not that. Your goal seems to just sample positions from that and not move the molecular dynamics faster. Is that right?
Yep. So that's a good observation. So that is indeed right. So we motivated the problem by saying that sampling was hard and we want to move faster. But actually, we consider the sampling problem to be the fundamental problem and moving faster as a sub-problem that we solve in order to target the sampling problem. And it turns out, indeed, we do not end up with a model that does kinetics properly. It's only going to be used for equilibrium sampling.
I mean, saying that it is the most important, the more important problem, like, is not necessarily right. But yeah, in most, not in most, but like in many instances of molecular dynamics, the goal is to sample from the distribution, but in other cases it is not, right? It's indeed one of the most important goals. So yeah, it makes sense that you do this assumption.
Yeah, I'd say it's a problem scoping issue. So we decided to scope it this way, and I'm not going to say that equilibrium sampling is more or less important than kinetics, but this is just how we scoped this particular project. Yeah. And yes, we did try learning velocities, and that didn't work. And actually, not learning velocities caused an improvement. I think you have a hand raised. Do you want to say something?
Yeah, I have one specific question. So, was your plan from the start that you want to learn the Boltzmann distributional sample from the Boltzmann distribution, or was first the problem, okay, I want to increase the time step and I want to learn the acceleration and then have this all atom simulation more or less with a bigger.
The plan from the start was always Boltzmann sampling.
Okay.
And large time steps was always seen as a means to an end. Yeah. Okay, cool.
But let's maybe moderate the questions a bit more and remember them in the chat, so we can have some other details as well that I think many people are interested in.
Yeah, so I might zoom a bit because we still need to get to the experiment section, which is the most interesting. So so what we're going to do is target this joint distribution, which has one factor for the true position marginal and one made up factor for the independent Gaussian velocities. And we're going to target this joint and then throw away the velocities. And so we'll target the marginal by doing this. Why augment? Well, first of all, it allows us to have a more expressive distribution for the positions without making the flow more complicated. And secondly, it turns out that it's easier for us to incorporate permutation symmetry by augmenting things in this way with the real MVP architecture. So let me just quickly go through what the MCMC algorithm is. So first, we sample a new state from the conditional distribution. And the state here is the position and the velocity. It's a tuple. Next, we compute the acceptance ratio, where the acceptance ratio is standard metropolis Hastings applied to the augmented distribution. In step 3, we accept or reject the sample using the standard acceptance criterion from metropolis Hastings. And finally, we perform a Gibbs update, which is very similar to what happens in Hamiltonian Monte Carlo, where in this case, we know the true marginal of the augmented velocities. So we resample them from the standard Gaussian distribution. Now, this seems painful and sequential because what's going to happen is you need to perform a forward pass for every single step. But we also introduce a batching algorithm for this. And I'm not going to walk through this pseudocode because there's too many lines, but there's a little diagram on the right, which hopefully gives you the idea. We can sample a batch of B proposals from the model with one forward pass. We can compute their acceptance probabilities. And here, like green represents high acceptance probability and orange represents low acceptance probability. And then we can just take the first accepted sample and append everything up to that point to the chain, all in one go. And this is very useful if your acceptance rate is low, for us to be 1 to 2%. So if we can sample a batch of 100 at a time, this really speeds things up because we need one forward pass instead of 100 forward passes. So
is that also included in your comparison with MD?
Yes. Yeah. So we basically increase the batch size until things are efficient, and then we use that in our comparison.
Okay, and if I wanted to know the comparison without this batching procedure, I would have to think about your method being 100 times slower.
I'd say roughly 100 times slower. Yeah.
Okay.
Okay, so that's the batching bit. And then now we also consider like an exploration algorithm. So it turns out that sometimes we can have very low acceptance, and it's an interesting thing to consider accepting all proposals and seeing what happens. Not every proposal will reject some proposals with extremely high energy, but other than that, we don't actually use metropolis Hastings. This is going to lead to bias. We're not going to respect the true Boltzmann distribution, but it turns out this gives us an algorithm for exploring metastable states much faster. So this is kind of throwing caution to the wind and seeing, can we explore quickly without guarantees? So that's the second algorithm we consider. And finally, the training objective. I won't go into too much detail, but basically, we train using maximum likelihood, using the data that we saw previously. And we sometimes also train on an acceptance objective, which I won't go through the details here, but basically we try to maximize the acceptance probability using energy-based training. But I think now is probably a good time to get to the experiments. And Leon, you can start sharing.
Yeah, thanks. You should be able to see my screen now, right?
Yep.
Yeah. Great. So yeah, let's talk about the experiments. So we'll show you the results for dipeptides, so consisting of 2 amino acids. Then the total number of possible combination is 400, and we train on half of them with this time step of 500 picoseconds. And the second more challenging data set we are looking at are tetrapeptides consisting of 4 amino acids. So now there are 20 to the power 4 possible configurations, and we train only on 1% of these, which are 1,500 tetrapeptides. And here we use a smaller time step in order to get higher acceptance probabilities. So here we show the training data. So what we'll show a lot for these experiments are so-called TICA plots, TICA projections. And what you can think of these 2D plots is that they're showing different metastable states. These are these blobs here. And transitions between these metastable states are slow. And we'll usually have a reference, which is generated by a long MD trajectory to compute this TICA projection. Then we'll use the same projection for here, for example, the training trajectories, but these could also be results from the Timewarp model. So what we can see here on the left is the metastable states found with the long MD trajectory. And in the right column, we can see that for the short training trajectories we use for the training, we actually miss several metastable states. So especially here in the lower half, we miss actually most of the metastable states. But because we're using so many peptides in the training, the idea is that the model still can learn to sample the correct distribution. But of course, this training data is fast to generate, but has, of course, some limitation, which makes the whole problem even more difficult. So from now on, all the results I'm showing are on test peptides. So they were neither seen in a training nor the validation process.
Jan, what are the parameters that you use as input to compute the TICA?
So this is based on distances between atoms, and we are considering the heavy atoms from the peptides.
Okay, so you use all the pairwise.
And also, yeah, all atoms, and actually also some important angles. Yeah.
But there are like other parameters to computing TICA, right? Like time lag and so on.
Yeah,
Is that
and
important?
Yeah, these plots might change a little bit based on the time lag you're choosing. Yeah, that's true. But for the time lags we're looking here, not so much. So the ordering of these states might be different, but you will see the same metastable states.
And just to say that, like, the TICA projection matrix is learned always on the MD trajectory, like a
exactly.
reference trajectory, never based on the model.
Yeah, that's an important thing.
You take the whole 50 nanoseconds of MD, and then compute the TICAs from there.
But no, sorry. This was what Andrew meant. So we are always computing the TICA projection based on the long MD trajectory. So this gives us the projection. And then for the short trajectories, we simply use this model computed for the long MD trajectory to compute the states. So here, if we want to compare these, this is very good. So here we'll see always if we are missing metastable states or not with respect to the long MD trajectory.
Yeah, and now, but yeah, if you say missing metastable states, how do you actually determine that your MD has already found all the metastable states?
Yeah, this we don't know. This just we think that we simulated long enough, but we'll see later that this might not always be the case. But okay. I mean, there's no way to know this. We just know that if we would sample for infinite time, then we would find all.
And are there any other input parameters that one has to consider when computing these TICAs? Because I know that like if we have T's, N's or so, stuff like that, then it's always very important to have every parameter right, or every parameter changes things a lot. So are there other
That's
parameters
true.
here?
Not that I can think of now, but importantly, as we're using the same Tika projection, and we're
that's
using
clear.
the same parameters, we can still compare this quite well.
Yeah. Okay.
Okay, so now these are test peptides, and the goal was to learn this conditional distribution. And so here we'll see some examples. So the leftmost column is again the long MD trajectory we used to compute the Tika projection. And then these two are conditional distributions generated by MD and by the Timewarp model. So for the Timewarp model, these conditional distributions are easy to generate. We start in one position here marked with the red X, and then we simply do one step with the model, a batchwise step to generate these plots, and then project them with this Tika projection. For MD, we have to run many chains, all starting from this conditioning state, and then we only report the final state. And you can see,
are all of these points in Timewarp accepted points?
No, this is just what the model proposed. So this is the learned distribution by the model.
Okay, yeah.
And so, but you can see, although they are not accepted, it looks very close to the MD distribution. And this can be also seen if we project them. These match quite well, especially here for the tetrapeptides. It nearly matches exactly. But now you'll see that they're indeed different if you look at the energies of these samples. So there you can see the energy of the Timewarp samples is a little higher than the MD samples. And that's why if we want to sample unbiased from our Boltzmann distribution, that we need to combine this with the Metropolis-Hastings step. Yeah, and then another little unrelated quantity are the bond lengths. So for the large time steps we are looking at, the bond length distribution should not depend on the conditioning state. And this is very well reflected by the model. So a single model step will produce a bond length distribution which is independent on the conditioning state. And yeah, so these are the acceptance probabilities for the peptides in the two different data sets. So as Andrew mentioned, they're around 1 or maybe below 1%. The tetrapeptides have a little higher acceptance probabilities because we are using the lower step time step.
Oh,
and this
I completely missed it. So yeah, I was now very surprised that for the tetrapeptides the acceptance ratio is higher, and that is because you have a smaller.
We use a 10 times smaller time step to train this.
Okay, just
a smaller tau, not delta T.
Exactly. Yeah.
Okay.
So
but your proposals are still super wide, as we saw on the previous plot.
Yeah.
Oh, given that your proposals are so wide, what do you think of the capability of this just as a Boltzmann generator? Like, what if we make our time step super large?
Yeah, we tried this. It didn't work that well for the experiments we did. So it seems to be quite important to have this conditional information for the model.
When you say you did try that, do you mean making the time step super large or having
essentially infinite? So the conditioning target pair was randomly drawn from the Boltzmann distribution.
Okay.
Yeah, but so it's a good suggestion. Yeah, it's interesting that the model requires the conditional information. It at least seems to be quite useful. And then if we now sample, there's the Timewarp model in combination with the Metropolis-Hastings steps. We again have here on the left the long MD trajectory, and then on the right-hand side here is the Tika projection of the trajectory of the Markov chain generated with a Timewarp model. And you can see here for these dipeptides, we find all metastable states. And also, if we look at the projection on the first two Tika components, which is the free energy, you can see that these match nearly exactly, only maybe for the transition state, they're a little different because there are so few samples. So, but what we're interested in is if we are faster than MD and sampling these distributions. And so to this end, we'll look at this dipeptide and start in the top left corner and run both the MD simulation as well as Timewarp in combination with MCMC for half an hour. And you can see MD, the samples are quite correlated, will stay long in these 4 metastable states, and transitions are quite rare. And for the Timewarp model, on the other hand, transitions are super common, and samples therefore way less correlated. And this is exactly what we're aiming for. So for dipeptides, the speed up in sampling from Boltzmann distribution works quite well. For tetrapeptides, it's a little more difficult. So here, see on the top is an example where it works quite well. We find all metastable states, but in the bottom one, we don't. And these simulations are run for roughly 2 days. And there our Timewarp simulation in combination with MCMC fails to find the slowest transition, at least to accept a sample along this slowest transition. And then the free energy projections match quite well, except, of course, when we miss states. So how do we compute now the speed up between the Timewarp MCMC and MD? And to this end, we compare the effective sample sizes per second, which are basically the uncorrelated samples per second generated with an algorithm. And we're here looking along this slowest Tika component, Tik0, and then we simply take the ratio and report this. And this effective sample size can be computed based on autocorrelations for different lag times. So you can see for dipeptides, we get a speed up compared to MD for most. So this walk clock time speed up. For some, it's lower, and for very few, it's super low. And this is here because for these dipeptides, there exists basically only a single metastable state. And that way, it's super hard to speed this up. And for the tetrapeptides, it doesn't work that well. So the gray areas where the Timewarp model in combination with MCMC does not find all metastable states. And for the rest of them, they are roughly for half. We see a speed up compared to MD. Yeah, there's a question.
Yeah, so with MD simulations, there are ways of also sampling better from the Boltzmann distribution. Like a simple way is just raising the temperature and lower it again, and these kind of things. Here, are you comparing just to vanilla MD simulation that runs by itself?
Yes, there's no enhanced sampling involved.
Okay.
For neither method.
Yeah. And yeah, so for the speed up, like, can you remind us, like here you look at the speed up in seconds, which is like the most important factor in real use case, but do you have also plots for speed up in terms of number of steps? Because like I know the MD simulation is probably much faster to run than your model. I think you mentioned 100 times faster, or is that correct? Or no?
So the 100 times faster referred to the batch MCMC we are doing. So what do you mean in terms of steps? So I think we can do roughly 100 or even 1,000 MD steps in the time of one model step.
Okay, so this would mean that if you have zero speed up in terms of number of confirmations number of states per second, you would technically still have 1,000 times improvement in terms of number of metastate per number of steps that you run. And in an ideal world, just making the model faster without without changing anything, would give you the speed up that you need.
Yeah. Yeah, and it's important to note the MD simulations will produce a lot more states than we generate with the Timewarp model, but these states are much more correlated, as we saw, for example, for this dipeptide.
Okay,
So-
perfect.
You go.
And if you go at the previous slide for
This one, right? Or not?
no, the one before. Yeah, so here you see that with Timewarp, you sample at many different places. Like if you run the simulation long enough, do you retrieve the same density that you would retrieve with the MD?
Exactly. Yeah. So this is what we. Oh, here we don't show energies, but the energies match exactly as well.
Okay. Yeah. Oh, yeah.
Yeah.
I see.
And-
This is what you showed here. Okay. Cool.
Yeah.
Hannes, you can go on.
I'm really not sure about this, so I'm just curious about your opinion. Should we actually here in these plots be comparing the one sample MD with one sample per batch MCMC, so where you do not do your batching strategy? So we just run one particle in MD and we run one particle in your method?
So you mean one chain MD versus our method without the batching?
Yep.
Yeah. This depends. So I think what you're saying makes sense if you look at the computational resources is required, because our model running parallel will require more resources than a single MD trajectory. However, it's not so easy to parallelize MD as it is to run our model in parallel.
Why not? Why can't we just start multiple particles?
So then it's a problem to get a single chain in the end. So multiple chains, or for example, multiple Markov chains cannot easily be combined into one long chain.
Fair.
Yeah, but it's true in terms of resources.
But
yeah.
What now if we just take a batch of 1,000? Like, is your model too big for that, or?
So the batch size, larger batch size, at some point don't speed up, because we only add to the Markov chain until the first sample accepted.
Yeah, but then we train with an even wider proposal, and we get an even
lower
lower
acceptance. Yeah,
rate.
Yeah. At some point, using a larger batch does not give an improvement. So then a batch size of 1,000 will take the same time as 10 times the batch size of 100, for example. So, yeah.
Yeah.
So
No,
that's the bottleneck there, but of course will depend on the compute infrastructure, probably.
How much RAM does it right now take to run your inference?
So I think we'll less than 10 gigabytes.
Okay.
Is that's about what we need.
Yeah.
5 to 10, I would say. I'm not completely sure. And this is mostly because of the model size, which is really large. The model alone is more than 1 gigabyte for the weights. Okay. And then Andrew also mentioned the exploration algorithm, where we accept all proposals. And so here, what's now comes in addition is the middle column. So what's interesting here, where Timewarp in combination with MCMC misses this metastable state, this actually explored if we do not reject states. And this also the case here for this middle thing. And the exploration algorithm runs much faster. There's no parallelization. So we run it only for about half an hour to an hour. And then these are the plots here we are reporting. And again, we can look at free energy projections. Then the exploration will be biased, but you can see here the free energy is still quite, or the free energy distribution matches quite closely to MD, although it's a little off. And also the energies are a little different. So here we see again that if we correct the time warp model with Metropolis Hastings, we receive or we'll get the correct energies. And with exploration, the energies are a little too high. And both these here can explain, if you remember, the conditional distribution from earlier, where this conditional distributions had energies which were slightly too high, but showed good transition rates between these metastable states. So we can compare them again. So this is MD, Timewarp MCMC, and the time warp with the exploration algorithm, all starting from the same state, running for half an hour. And you can see the exploration algorithm transitions first several times, while the other two mostly stay in the metastable state. And here the Timewarp MCMC eventually transitions as well. And the Timewarp, yeah.
Here your exploration mode also goes into this bottom left corner, where there is actually no mode, right?
Exactly. Excellent question. Yeah. So here we discover a metastable state that is not discovered by the other two methods.
Wow.
in 2 days.
How do you know this is a metastable state?
Yeah, exactly. We don't know. It doesn't have to be safe, so that's why we checked afterwards. So the idea would be, okay, the time warp exploration mode discovers your states, and the other algorithms we just didn't run long enough. But the concern is quite valid. Is this a valid metastable state? So we validate these states. So this happens for multiple tetrapeptides, as you can see here. These are 2 examples. So the exploration modes in both cases finds a state unexplored by the other methods. And what we do then, and this could be done different ways, that's just the way we pick, we basically, again, compute these conditional distribution plots. So we start from a metastable state discovered by the long MD trajectory, and different ones, actually. You can see here we start in different ones, and then you can see that some MD trajectories actually transition to this metastable states proposed by the time warp exploration algorithm, but initially missed by MD and Timewarp and MCMC. And this is the case for both. And the Timewarp model finds these as well, but these cannot necessarily be trusted, although this is the Timewarp. Okay,
so how do you reinitialize the MD?
So we look at the long MD trajectory, then we pick different metastable states that were explored there. For example, this one and this one, and then we start short MD trajectories from that until we find this metastable state proposed. And then we start trajectories again from these points proposed by or found with the short MD trajectories and run MD there again. And there we see that this actually a true metastable states where we most of the time stay in the state and then sometimes transition to other metastable states. And interestingly, the time warp model predicts exactly the same. So this again, the conditional distributions are basically a single forward path with the time warp model. So yeah, this also referring to what you asked before, right? If you, how do we know if we found all metastable states with MD? So this we don't know, but we have to terminate the trajectory at some points, especially as we are doing this for so many different peptides. And here, a great application of the time warp model would be to validate if such trajectories, it doesn't have to be MD, could also be with Timewarp MCMC actually found all metastable states or not.
So basically here, what you're saying is that your exploration algorithm found states that are difficult to transition to or to transition from. Like once you're in that state, you don't go out to others. And when you are in other states, you don't come to that one. But both are valid because when you start there, you stay there. So, okay.
Yeah.
Have you looked, for example, at like these discovered metastates if they tend to have higher or lower energy or than the regular?
The energy is actually quite similar. I think just
Okay.
the MD simulation wasn't run for long enough.
Yeah. But yeah, okay.
And this
Sometimes you see like in the MD simulations, for example, here you see 1 point that's there.
Oh, sorry. Yeah.
Or
yeah.
Yeah, so you see 1 point that's there, or here you see 2 points, but it
Mhm.
seems that it went back to the original distribution, perhaps because when it visited these points, the velocity was too high, or
Actually, okay, yeah, it's a good question. I think I didn't explain well enough how these plots are generated. We actually start in this state, and then we only report. So these are plots for many small, short MD trajectories, and we only report the last state. So this, yeah, this
So we always
yeah.
start at the red cross.
Exactly, and
And then we run the whole trajectory, and then once trajectory is complete, we plot 1 point.
Yeah.
Okay, so these plots contain thousands of MD trajectories, not thousands of points sampled from the trajectory, but thousands of MD trajectories. Okay.
Yeah, exactly. I mean, yeah, it's just one way to find these. We could also run longer ones. Yeah.
Okay, but I understood correctly, right? That in the plots in C, there you just start the MD simulation in one of those states.
No, it's again short trajectories actually. It's again many short trajectories. So all are started in this point, and then we report always the last point of these trajectories.
Yeah. But here you now start in the metastable state.
Exactly, found by a previous by one of these short MD trajectories. Yeah, exactly. Yeah. And so here we can compute the speed up similar to before, time of exploration versus MD, although of course the exploration mode now samples from a slightly different distribution, for example, with higher energies. And then the speed up factors are quite large for dipeptides between 100 and 1,000, and for tetrapeptides, the green area denotes where we find more metastable states than the long MD trajectory. And therefore, the other tetrapeptides, we have speedups between 10 and 100.
Is the effective samples per second here also done with your batching?
No, because we accept every sample.
Oh.
So there's no parallelism in this case.
What does it then mean to have an effective sample if we accept?
It's an effective sample from a different distribution. It's not from the Boltzmann distribution.
Okay, fair.
Yeah, but the distribution has a little too high energy, but finds all metastable states, for example. So it's a similar distribution, but not the true one. As you mentioned, yeah, we don't use any parallelism here, but we can. And so what we did in practice to check, for example, if all metastable states were found, is to run, for example, 100 of these exploration modes from the same conditional state in parallel, only for 5 to 10 minutes. And then we'll find all the different metastable states for these tetrapeptides. Okay, I think we are always a little over time, but there are a lot of good questions. So to sum things up, in the paper, we introduced the Timewarp model, which is a transferable model to predict future states of peptides. And we can combine this model with 2 sampling algorithms. One was with MCMC, and there we saw speedups for dipeptides and for some tetrapeptides or most dipeptides. And then we could also combine it with the exploration algorithm, where we do not accept and reject state except for very high energies. And there we saw a speed up for all the peptides, but at the cost at no longer sampling unbiased from the Boltzmann distribution. And there we saw that we could find all metastable states, which are indeed true metastable states, much faster than MD. Yeah, that's it from our side. Thanks a lot.
And that's been a lot from your side. A lot of very good stuff, in my opinion.
Thanks.
Yeah, thanks a lot. I have a question that was on the top of my mind for some times. Like you work with peptides, but your peptides are only 2 or 4 amino acids, which are basically the same size as small molecules. So why not just do small molecules? Why constrain yourself to peptides?
Good questions. I think the goal is to, at some point, sample from proteins. So that's why we looked at small proteins. But yeah, there's no reason it shouldn't work, for example, for other small molecules.
Yeah.
And maybe
so your goal
maybe
at some point is to expand to larger peptides, I guess? Or...
Yeah, exactly. Yeah.
And why do you think your model has more difficulty with the, or like less speed up with 4 amino acids than 2 amino acids?
I think just because there are more atoms involved. Maybe also because the training data has seen a smaller percentage of the possible configurations. And you have to do, the model needs to do a lot right in order to get reasonable energies.
Do you train on both the 2 amino acid and 4 amino acid in the same training set?
And no, we haven't done this. So these were different training runs. Okay. So we only predict on similar things with the same number of amino acids. But in theory, there should be possible. So there's no limitation for the model to only predict one type of peptide.
I think a great thing would be to look at the generalization of the model beyond the amino acids. Like, I mean, if you only train on 2, maybe it's a bit too difficult to generalize. But like, let's say if you train on 1, 2, 3, and you test on 4, 5, to see like compared to training with 4, 5, like I think it would give a much better picture on like how useful that model can be on general peptides.
Yeah, that's a great suggestion. Yeah, totally agree.
But thanks a lot for the presentation. I think like there's a lot of stuff. It's a great presentation, great work, and I know this kind of thing will come more and more in the future. This kind of work where we accelerate MD simulation. So congrats a lot, and beautiful presentation.
Thanks also a lot for having us.
Yeah, thanks. Glad you enjoyed it.
Okay, there are more questions. Please go ahead, Clemens.
Yeah, thanks a lot, Leon and Andrew. I also very much enjoyed that presentation. I was wondering, do you anticipate any challenges, or have you maybe already tried this, applied to multi-component systems, such as ligand-protein interactions?
Okay, I think, so we definitely haven't tried this. And this is definitely an interesting approach, but I think it's a much more difficult problem to have two systems than one. But I think in theory, this method could also work there.
Yeah, so like, for example, the model doesn't know, it's not a priori baked into the model what chemical bonds are. So the model simply knows where atoms are, what their 3D positions in space are. So in theory, you could take this whole framework and apply it to a data set of MD simulations with more than one molecule interacting. And you wouldn't have to change the code base to get this to work. We have not tried that.
Okay. Yeah. I think that could be very interesting as well. Cool, thanks.
Yeah.
as you could maybe tell, I find this paper great, and I hope you did so too. And if you want to join future reading group sessions, all the information is down in the description, and maybe see you on some Monday.